just the best gift I could have had, because I said, oh, fine, so all the work I did is right.
Here in San Francisco, the discovery was dramatically verified just this past weekend.
October 19th, 1995.
What may be the discovery of new planets outside our solar system has created enormous excitement among astronomers.
The confirmation was made before the official announcement of the discovery itself.
It went completely out of control.
Everybody was discussing of this new object, except us.
By tradition, scientists have their discoveries peer-reviewed by other scientists for accuracy.
I was one of the referees on the paper. There were 3 referees, and normally I think they only do 2, but this was so big that the Nature editor, Leslie Sage, was being very careful.
Because of the situations, Nature was very strict. They say, well, look, guys, if you talk to people, then we're not going to publish your paper.
So it's only after 1 month or something like this that I receive a message from Nature that, okay, no, you are relaxed from the embargo.
Because the discovery was just too big, just far too big to follow the usual scheme that is required for a scientific paper. As soon as you start talking about that, I mean, everybody wanted to know about this.
51 Peg B is a real planet, no question about that.
As soon as we detected 51 Peg, he had on his data plenty of something like that. You just need to look at it.
At this point, we hadn't analyzed all our data. We had 2 computers, and it would have literally have taken us 5 or 6 years to get through all of the data. So literally about a half a dozen different groups said, you know, we've just received these new computers, and we're not going to use them for the next several months. You want to dump your jobs on it.
Within 2 months, 2 other Jupiters circling around their stars were found by Marcy and Butler, and the floodgates of planet hunting were now wide open.
You know, from no planets at all to the point where we're discovering a new planet every month or even sometimes every week. And almost all of the planetary systems that we found were very different from the solar system, weren't even similar in the least bit.
I remember asking at a meeting, you know, how long do you think this will go on? And I think Michelle Mayor said, oh, maybe, you know, another 5 or 10 years, and then the game is over. Fortunately, the game just got a lot more exciting.
After getting my PhD, I became aware of this fellow at NASA Ames Research Center, Bill Barucki.
I would see him at all these meetings. They were very small meetings back in the day. And like he'd literally be by himself out having dinner, so we would join him and chat about things, and he was very persistent.
Bill walked around the halls, and whenever the Ames managers saw him coming, they turned and walked the other way.
Bill Barucki wrote a paper in the 1980s that described the transit method. When that planet passes in front of the starlight drops by a tiny, tiny amount. And by measuring the brightness of the star, minute by minute, we can detect planets going in front of the star, and we call that the transit method. And detectors that could measure that precise drop in brightness didn't exist yet.
To be successful, all one needed to do was build a photometer 1,000 times better than anyone ever built one. But I'd worked on the Apollo program, I'd worked on other programs, so that's not really that scary. You just need to get down to brass tacks and find out what's required and build it. There just is no way of finding small planets in orbits like that of the Earth unless you go into space. You must go into space.
He kept getting shot down by the review panels for various reasons, and each time he'd fix the reason and go back a second time, and they basically said it's not going to work. Well, Bill Barucki didn't bother reading that report, or at least did not take it to heart. Kept on his crusade to show that transit detection should work.
He was able to demonstrate in the lab that he could measure the precision required to find Earth-sized planets orbiting sun-like stars.
Some people call it stubbornness, but the point is I knew it would work.
So he proposed and reproposed, and eventually he conceived of a Discovery-class mission that was later called Kepler.
It was 25 years between the date of publication and the date that Kepler actually launched.
1-0 and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Kepler just delivered so much tremendously new things we never even conceived of. And the things that were on our wish list, Kepler found for us.
This data was being displayed for the first time on the computer monitors. And there was the transit of that Jupiter-sized planet, and the data was like beads on a string.
Kepler has transformed our understanding of exoplanets. What Kepler was designed to do specifically was to go after terrestrial or rocky planets that are in closer orbits to stars. We now know from the Kepler data that planets like the Earth are in fact common in the galaxy, and that's something we fundamentally didn't know before Kepler.
The first exoplanet was already diverse, and Kepler continued to find more and more planets that didn't fit the norm, both in size, in composition, in distance from their stars. So when you think about how many stars there are in our galaxy, there are a few hundred billion, and if each one has one or maybe more, we're looking at a few 100 billion planets.
To accomplish something great, you have to have persistence.
To succeed in exoplanets, we have to be very ambitious and very bold.
Kepler's impact was extreme, certainly more than I'd ever imagined. It's basically opened up an entire new era of astronomy.
Now that we know that the galaxy is teeming with planets, we are ready to go to the next chapter of planetary exploration.
I truly believe that the 2020s are shaping up to be a golden age for observational astrophysics. You know, we have these amazing telescopes like TESS, the Transiting Exoplanet Survey Satellite. We have WFIRST, which is this Hubble-sized telescope that can see 100 times as much of the sky in each image. We have the James Webb Space Telescope, which is, you know, the largest and most powerful telescope we've ever built. You know, the reason that we can even dream about that and create something like that is because of the success of Spitzer and Hubble and the previous great observatories.
I'm looking forward to space-based missions where they're going to have coronagraph technology and maybe even star shield technology in order to image exoplanets by blocking out the light from stars.
And we have the next generation large 30-meter class telescopes on the ground, which are going to be coming online in the 2020s. But the question that has me most excited about the future of astronomy is to answer the question, are we alone in the universe?
Finding evidence of life on an exoplanet, finding an indication of a living world, is within our reach.
What is life? Life is a process to transfer information from one generation to another.
Everybody is interested in the search for planets, the search for places that remind us of home.
We're looking for some hint of our origins, where we came from, and exoplanets may very well provide that context.
There may be more habitable real estate out there beyond our solar system than we once thought.
I think we're naturally curious to find out if there are other conditions in the universe that might be similar to our own. And finding exoplanets around other stars is the first important clue.
The search for planets is a search for life. And even though we didn't really say that out loud, that was always in the back of our minds.